Well, good afternoon, good day, everyone. Welcome to the fourth webinar of the A-GaME webinar series. And this webinar is on outcomes as a sort of a special series or a special webinar coinciding with the EDC 6 Summit, which maybe you have been able to get to earlier today and maybe later on today. So the topic of today being on outcomes, we've got three speakers lined up for you today. We've got Jeff Reed with Hager Richter, Jesse Rouser with Louisiana DOTD, and Jeff Curry with Alaska Department of Transportation and Public Facilities. And so we're wanting to showcase sort of the value side of the A-GaME. So within these presentations, I hope you can look for some of these bulleted items and look for how we can make site characterization more effective with the techniques being described today and some of the examples that are going to be shared, showing you some tangible examples of return on investment may not be necessarily quantitative that we see here, but it could be better site coverage, targeted data that certainly adds value. The communication side, obviously the reliability of construction and design is a ultimate one of the goals of the A-GaME, and efficiency as well. So look for those examples and other values as we go through this webinar today. I am going to stop my sharing here, and I'm going to introduce our first speaker. And Jeff, you can go ahead and get your presentation loaded up. Jeff Reed is a geophysicist with Hager Richter. Mr. Reed has over 33 years of experience in geophysical, in the geophysical profession. He's been involved with all aspects of Hager Richter's geophysical project work since the earliest parts of the firm's history. Mr. Reed has acted as lead geophysicist and has led field crews for thousands of surface and borehole geophysical surveys and project fieldwork. The surveys have included borehole geophysical logging, seismic refraction, reflection surveys, electrical resistivity imaging, gravity, self-potential, very low frequency electromagnetics, ground penetrating radar, magnetics, and electromagnetics. The work typically requires close coordination with engineers, owners, regulators, requiring multiple progress meetings with stakeholders. Mr. Reed is also often an invited speaker on geophysical topics and has been instrumental member of our A-GaME implementation team in helping us roll the A-GaME out. So with that, Jeff, I'll turn it over to you, sir.
Thanks, Ben. Appreciate it. So as Ben indicated, I'm going to be giving you a brief introduction to a few of the A-GaME methods and a series of 3 case studies where they've been applied, and I hope I can show that the significant value has been added to the subsurface investigation programs. First, I'd like to start just going through a quick discussion of the benefits of geophysics, how it's used on transportation projects, and how it can add benefit or value to the projects. So the benefits are, well, first we'll say it's basically you're reducing the unknown. According to FHWA, 50% of major infrastructure projects will be significantly impacted by geotechnical issues. namely a lack of geotechnical information in the subsurface. Many of these issues would be directly or indirectly related to the scope and the quality of the initial subsurface investigation or characterization. This is where geophysics and some of the other A-GaME methods can significantly bridge the gap, adding additional information to the subsurface investigation to remove risk, to remove uncertainty, and to, in the end game, save cost. Technical benefits are listed: improved site subsurface characterization, additional information between borings and test pits, and better information for foundation and structure designs. The non-technical risks all come down to cost essentially, but they reduce drilling cost, less environmental impact, more appropriate design, more accurate bids, and few unexpected conditions and change conditions, which ultimately reduce the risk for the owner. The surface geophysical methods that we rely on for the A-GaME program are electrical resistivity imaging and the seismic methods. Some other widely used or more regularly used geophysical methods for transportation projects: ground penetrating radar, electromagnetic induction, magnetics, and utility location. I'm going to focus on the A-GaME methods and for the sake of time, not really go into depth on the other methods. Electrical resistivity. It's widely used for determining characteristics of shallow geologic layers, identifying peat, clay, sand, silt, and till in the subsurface, and also finding geohazards like voids, caves, and karst. It's also widely used for depth of shallow bedrock, depth of water table, and for locating man-made features like tunnels and other structures in the subsurface. Limitations of the method. I think it's very important to understand what the limitations are of each of the methods so that it is used appropriately and in the right site conditions. Surface conditions can significantly limit the effectiveness of electrical resistivity of all geophysics, but electrical resistivity. Water, snow, ice, vegetation, and uneven ground surfaces can impact the quality of the data and impact where you can acquire data. Subsurface conductive utilities impact the quality of the data. If you are too close to subsurface utilities, you can essentially short circuit the system, and the information you receive or the information you try to use for your interpretation is invalid. The method relies on contrast in electrical resistivity between your medium and your target. If you have a strong contrast, detection is relatively straightforward. If you have a very weak contrast, detection is difficult. A good example of that would be trying to identify a very highly resistive bedrock underneath a relatively conductive clay. It's relatively easy to do. Trying to identify a boulder within a dry sand, there's very little contrast between the two, and therefore detection is difficult. One key with geophysics: detection is not identification. We can detect a lot of features. We cannot necessarily identify what the features are. If we do not have ground control or ground truth through borings, then it's strictly a coarse interpretation. That's why geophysics is typically used to fill in data gaps between borings rather than on its own. It can significantly extend your point data. Depth of investigation versus lateral and vertical resolution is a key component of electrical resistivity. Small objects at great depth are very difficult to identify, as well as small objects when you're trying to see very deep. The deeper you're looking, the lower the lateral and lower the vertical resolution is. The shallower you're looking, the higher the resolution. So it's being sure that you are targeting your investigation to match the objectives of the survey. And accuracy and depths of the ground and ground truth. You require boring information in order to provide a more meaningful interpretation. Seismic methods, seismic refraction. There are specialized methods: MassDOT, refraction, microtremor, and horizontal vertical ratio. And borehole methods: parallel seismic and crosshole seismic. For this presentation, I'm only going to discuss the refraction, traditional and tomography, and the H/V for the specialized methods. There'll be a webinar next week, 2 webinars next week that will address both seismic methods and electrical methods, so you can get a much more in-depth discussion of those next week. Seismic refraction, it's the industry standard for determining the depth and configuration of the bedrock surface. Most widely used, and it is the most effective way to do it. You also determine the velocity of the bedrock for rippability surveys, depth of overburden layer interfaces such as till or water table, the velocity of the overburden materials, if that's of information to you, that's compression wave velocity, and then again, depth of water table. Limitations for refraction, surface obstructions are again a limitation. You need to have access to the area where the data are to be acquired. Ambient seismic noise is a significant limitation, especially for transportation-related projects. There are vehicles, subsurface noise from tunnels, from other structures, from bridge piers that transmit signal down into the ground. These all impact the quality of the seismic refraction data, and have to find ways around them. Typically, we would work off hours, or you'd have restricted traffic. You try to find ways to limit ambient noise so that the noise we're generating for the data or for the acquisition are dominant. Frost and snow and other subsurface man-made features can significantly impact the quality of the data. Typically here in the Northeast, we tell people once you get 1 foot to 1.5 feet of frost, we'd prefer to wait till spring to try and acquire data, just because it can act as a significant filter and negatively impact the quality of your data. High tension lines can add significant electrical noise if the high tension lines aren't well grounded and there's leakage. Depth of investigation, again, that kind of goes back to your surface obstructions as well, though. You need a certain length of line in order to see as deeply as you need to see. The more deeply you need to see, the longer the line setups are, and the more access you need on the ground surface. Accuracy and ground truth, standard accuracy of the method is stated as about 10% or plus or minus 10%, or 2 feet, whichever is greater. We don't recommend conducting refraction when bedrock depth is less than about 5 feet, better above 10 feet. We can use other methods if it's shallower than that to more accurately define the surface. And you can detect bedrock as deep as 200, 250 feet with refraction. Specialized method, the one I'm going to discuss here is the horizontal to vertical spectral ratio, because it is used in one of my examples. It's a cruder method for determining the depth of bedrock in areas where you really simply have no other way to do it. And it'll become obvious in my example why it was used here. It's a very useful tool, and it's very quick. It's very easy, and it gives you a good assessment of the depth of bedrock, probably to within 15 or 20%. That could be better or worse, depending on what kind of ground truth you have in the area to calibrate with. But it's a great tool where simply nothing else will work, usually due to access reasons. And limitations, these are essentially the same limitations as the seismic methods, the seismic refraction methods, so I'm not going to go over them here. And then borehole geophysics. So to this point, we've only talked about methods from the surface. These are now acquired in boreholes. They're installed. So it's more point source data. And specifically, we're going to talk about acoustic and optical televiewer logging. ATV and OTV, as they're known as, acoustic and optical televiewer logging, are used widely for rock slope stability surveys for determining the depth and orientations of bedrock fractures, foliations, bedding, your fracture aperture, and changes in lithology in the boring. You're physically imaging the in-situ borehole wall. It's also used for inspection of subsurface structures, quality of concrete, bedrock or concrete, whatever interface you're mating with. It can give you a very good image of that contact, that interface. Limitations. Obviously, it's a borehole tool that requires an open borehole. For ATV and OTV logging, centralization is key, so we require at least a 3-inch diameter borehole, obviously open borehole. ATV can only be acquired in the fluid-filled portion of a borehole. The fluid does not have to be optically clear. It doesn't have to be water. It can be a slurry. It could be oil. It could be water. It doesn't matter. It just has to be in a fluid. OTV, on the other hand, requires optically clear fluid or air-filled borehole for acquisition. We we always acquire both ATV and OTV because they often complement each other. There may be portions of the borehole that are dry where you can't get acoustic televiewer data. You have the optical data, or you have optically clear fluid for a portion of the borehole and not for the rest of the hole. So the ATV data will take over for that. And you'll see some examples for that as well. And just a quick tutorial on what you're seeing when we do look at the logs. You've got here is the borehole, and you've got the red plane passing through the borehole. As that plane passes through the borehole and you unwrap the image, as what we're looking at with the ATV and OTV data is an unwrapped image of the interior of the borehole wall. A horizontal plane would produce a horizontal plane on the unwrapped image. A vertical plane that passes through the core hole would present a vertical line on the unwrapped image. But any plane that passes through the cylinder at an angle will produce a sinusoidal wave. By measuring the amplitude or the width of the sinusoid, you get the amplitude of the anomaly, and by looking at either the peak or the trough location, it gives you the orientation of the plane. These, the optical and acoustic televiewers have deviation probes built within them so that we know the true orientation of the cylinder. A vertical hole is never vertical. There's always deviation, and it uses that data to properly correct the sinusoidal waves that we're seeing so that we're getting true strike and dip, or strike and dip azimuth of the, or dip and dip azimuth, I'm sorry, of the plane as it passes through the borehole. And then this is just simply using that same image, but using an actual acoustic televiewer log. This is the amplitude log from the acoustic televiewer. This is a rewrapped core image of the borehole, and then the unwrapped image. And you can see you've got a plane here at an angle, and you get the sinusoidal wave. So again, by looking at that amplitude and its position within the 360-degree compass, it gives you the orientation of that plane. Okay, now I've got 3 case studies to go over with you. First case study is a bridge replacement project in Massachusetts. This was done for MassDOT, the MassDOT bridge program and its representatives. The objectives of the survey were to determine the depth and configuration of the bedrock surface, both at the approaches for the new bridge and in the river for the actual span itself. They needed wave velocities for soil and bedrock for seismic design, evaluation of the river floor for the presence of obstruction to construction along the possible alignments. So geophysics here was brought in very early in the project, or in the planning stage, even before actual design, and in the planning stage. So it could be, you're getting the best bang for your buck, the most value, because you're allowing yourself to use the data to actually get yourself to a design stage with more information than you normally would, rather than coming up with a design and then looking at the geophysics to try and confirm it. The methods that were used in this case were seismic refraction for the land, seismic reflection in the water, bathymetry, side-scan sonar, and magnetics, and passive shear wave velocity testing at the locations of the planned abutments for seismic design. We conducted the land portion of the seismic and the passive shear wave, and we worked with E4 Sciences to who actually acquired the seismic reflection and bathymetry and side-scan sonar. This shows basically the data paths for the water-based geophysics or marine geophysics. Each of these are the different scans that were acquired, obviously from boats within the river for the side scan, the magnetics, and the reflection seismology. This is a resulting water surface or river floor map based on bathymetry and side scan sonar. These purple lines show the 3 possible bridge paths that the DOT was assessing for for the alignments. The existing bridge was a temporary bridge, and it's been there about for 40 years, and it's finally being replaced. So we did have some information from the existing installation. The data for those borings were used for calibration, and then that data were extended to the rest of the interpretation to provide, again, extending that information away from the existing borings by using the geophysics. This is an example of one of the seismic reflection profiles. You've got the water floor or the river floor here. You've got just mud and other material up above, till layer, and then the hard granite below that, and even some fracturing from within the granite below that. And these were the borings provided by DOT that were used for calibration and then extended out. This is some of the land geophysics. So again, long arrays set out along the path where the approaches were due to come ashore, using a accelerated weight drop as a source, resulting seismic refraction profile. So unsaturated soils over saturated soils and tills over competent bedrock. And you can see where the bridge was coming out here, and this was the line on either side. And by taking both the surface and water-based geophysics and the depth of bedrock, and in the water portion, at least the depth of till, you're able to generate bedrock contour maps. This is a till contour map. This is a bedrock contour map, which helps decide or helps choose which alignment is most appropriate and most cost-effective for the new bridge. Second case study, this is a slope failure on Pennsylvania State Road 87, which is in north central Pennsylvania. This was for PennDOT District 3 and its representatives. The objective of the surveys were to determine the depth and configuration of the bedrock surface, both above the existing roadway and below the existing roadway where the slope mitigation was going to happen, and to detect a possible bedrock shear zone that bisects the failed slope based on observations from outcrops and topography above the existing roadway. This roadway experienced significant settling and failure after a couple of very heavy rain events a few years back. The existing drainage was working adequately, but it was clear that water was actually moving under the roadway rather than through the drainage system as originally designed. The geophysical survey consisted of seismic refraction tomography, standard seismic as well, and electrical resistivity imaging. Here's the site. So this is a rather large hillside here. You've got a brook that's down below. So you've got all the water moving under the roadway in this location. It's a site plan. So this is the higher side. This is the lower side. The stream would be down below. And you've got resistivity and seismic refraction along this line, and just seismic refraction along the bottom side. We could not run electrical resistivity down here due to pieces of guardrail and other utilities that were impacting, that would have impacted the quality of the data. Here's a picture of the roadway. So we've got the electrical resistivity imaging set out in this case. The electrodes in the ground here. And you can see the failure on the opposite side of the road here. And this is a view. You can actually see the anticipated shear zone, and there are outcrops up here that were mapped by the geotechnical consultant we were working for and indicated there possible is a shear zone in this low area. So the electrical resistivity line was actually centered on that feature. This is a surface seismic refraction tomogram. It's tomography. So the varying colors indicate changes in velocity in the subsurface. Blue colors are low velocity, reds and purple colors are high velocity. The lower plot is the resistivity image. Greens and blues are low resistivity, meaning conductive features. And reds and yellows are high resistivity, meaning resistive features. This particular line was centered on the location of the possible shear zone, which was located off center from this catch basin. They had clay and PVC pipes extending out from the catch basins. They don't impact negatively the data. Very low resistivity feature just above bedrock on the side of the road. And this is the tomogram. You don't get a significant feature here, but you do get a dip in the bedrock surface and a slight change in the resistivity. I'm sorry, in the compression wave velocity of the bedrock. This is the view of the seismic refraction on the opposite side of the road. So the refraction were actually run in segments that came down in the slope below it. And this is a view of some of the bedrock, very shallow bedrock, which would have been up in this area over here. And again, this is a seismic refraction tomography. The dashed line on here actually is a standard refraction interpretation. It's called the generalized reciprocal method. So it's a layered interpretation versus a tomogram, which allows you to image and process it as a continuing change in velocity versus depth. The two match very well. And these are the boring logs that indicate depth to rock. And again, you're extending that information between the two models. Last study. This is a rockfall mitigation project on Interstate 80 in Hardwick, Knowlton, New Jersey. The objectives of the geophysical survey were to determine the approximate depth of bedrock below talus piles and along difficult slopes where drilling was very difficult. You'll see, it'll become obvious in a moment. And to determine the depth and orientation of bedrock fractures for use in the slope stability analysis. So here we use seismic refraction, horizontal to vertical spectral ratio, and optical and acoustic televiewer logging. Site's located very close to the New Jersey-Pennsylvania border on I-80. There's a significant rock outcrop that occurs right along in here. It extends along the roadway with a significant talus pile below it where rock is coming down off of it. So they're trying to design a mitigation system for these rock falls. This is a view looking to the east from the slope. This huge talus pile from the rock falling from above. These are the areas where we use the H/V, where it's pretty clear that drilling is not possible, and refraction, seismic refraction, conventional refraction is not possible in areas with steep, hard talus like this. We did run refraction in the wood lines where we had soil infilling around the talus, where we could acquire good quality data. Obviously, noise is a significant issue when you're working along an interstate highway, and most of the work was done in off hours and at night, and actually with traffic minimized to a single lane to slow it and minimize noise impact to our data. This is a blow up of one of the sections. Again, just seismic refraction along areas where we could have access to it. And you can see that in this blow up, or sorry, the scaled out view, there's significant distance between those lines where we couldn't acquire data. That's where the talus existed, and that's where we did acquire H/V data. Again, very similar to the last profile that we presented. In this case, only GRM, or only a layered interpretation. Simple unsaturated soils over competent bedrock. But this profile then can be used to help design footings for the mitigation. In addition, we acquired the H/V, which it's about the size of a small shoebox. Gets set down and records data for about 17 to 20 minutes, both the horizontal and vertical components of the seismic waves. We use an inversion scheme to then look at that data and determine a bedrock depth based on the ratio of the two forms of the seismic waves. And it gives us an estimate of the overburden thickness at that location. In this case, we did it at 44 different locations along the talus pile, and also acquired it at locations where we had known depths of bedrock to calibrate the ratio that we're seeing, and then you apply that equation across all of the data points to generate a bedrock topography map for for the area under the talus pile. There's no other way you could generate this without extreme cost for drilling. They did put in some of the borings, as I showed you on the last plot, but you could see how they had to basically build platforms into the talus pile for supporting the drill rig. We went and acquired acoustic and optical televiewer in all of the boreholes that were installed here. In most cases, we had the equipment hauled up to the top. It's a little hard to carry it up. And see, these are some of the geophysical borehole logs. So again, you've got the optical televiewer log here. You've got the acoustic amplitude plot here. And you've got the acoustic travel time plot here. This is the caliper plot generated from the acoustic travel time. So it gives you the borehole diameter. Tadpole structure plots provided on top of the image. So each one of these individual features, which are categorized by their fracture rank. Fracture rank 1 would be a partially connected around the borehole with no aperture. Fracture rank 2 would be completely wraps around the borehole, but with minimal aperture. And then fracture rank 3 and 4 both have aperture. Fracture rank 4 has significant aperture. Then the rewrapped cores here as well. You can see the bottom of the casing in the optical image is set into the rock. In this particular case, the casing was supposed to be extended down to 9 feet. It was over drilled to provide access to the casing to get it down to this position. But you can see the casing got trapped above it, and there's actually a gap, significant gap in the rock above that. Quite often that can pose significant issues for collapsing of the borehole. And you can decipher in these large zones many significant fractures. The cores for these particular holes were basically coming up in very small chunks. You could imagine that the RQD was poor, as was the recovery. So trying to get an accurate image of the fracture statistics from a core for this site is very difficult. But when you're dealing with an in situ borehole wall, you've removed all of the ambiguity from mechanical versus natural fractures that you'd have in a core, because you are simply looking at the borehole wall. From that, we can generate the stereograms, dip rose azimuths, and dip histograms. In this particular case, you've got a steeply dipping set of bedrock fractures that happens to be parallel to the foliation. And you've got a secondary set of fractures that are essentially 180 degrees to the foliation and are very steeply dipping. These data can be used then by the geotechnical engineers to determine the slope failure mechanisms that would be expected when they try to build their structure. That's it from me. So I'm going to hand it back over to Ben, and he can take it from here.
Good. Thank you very much, Jeff. That's an awesome presentation. And a great example of a difficult condition where certainly this geophysics fits the bill. In conditions where you just can't drill anywhere, and great example of that. So very good. So I will let Jesse start his screen while I introduce Jesse Rouser. Jesse is the Assistant Geotechnical Administrator for Louisiana DOTD Geotechnical Group. He has worked with the department for about 10 years and worked in the private sector before that for about 8 years. He graduated from Louisiana State University in 2003 with his bachelor's in civil engineering, and in 2008 he received his master's in geotechnical engineering. His interests include deep foundation design, testing, and data management. With that, Jesse, I'll let you take the floor.
All right, thanks a lot, Ben. Am I showing the correct screen here?
Yes, you are.
All right, cool. So I'm gonna go ahead and jump right into this. tell you guys about some of the CPT research that we've done here at DOTD. And so to anybody who's doing CPT during their everyday processes, this is all going to be kind of elementary stuff, but I just wanted to kind of demonstrate that CPT definitely has a place in the repertoire, and it's got a lot of advantage over traditional soil boring. So, you know, I look at it as a pretty much equivalent tool, or it should be used, you know, 50-50 if you can manage it, at least in my opinion, on our projects. So moving right along, you know, LSU and the LTRC, which is the Louisiana Transportation Research Center, they started researching the applications of CPT for Louisiana transportation projects back in the 80s. And then this slide here just kind of shows some of the projects where we researched cones and mini cones on just various transportation applications. And then in the late 80s, Dr. Zhang and Tumai, they had a research project where they looked at an alternative statistical approach to classifying soils using CPT. And so instead of breaking things up into different soil behavior types, it basically split everything into 3 categories, and it was more of a statistical type of approach. So it looked into, you know, what's the probability that we have clay, silt, or sand? And then later on in the 90s, TD and Abu Farsak researched some of the direct pile design methods that were out there. And these are methods where you're not converting CPT into intermediate steps. You're basically just using these methods to estimate pile resistance directly from the CPT data. And so they looked at 8 different methods, and they ended up picking the best 4 for the data set that we had here for Louisiana soils. You know, those methods, those 4 best methods, along with that statistical classification methodology, were incorporated into a Windows software that could be used to estimate power resistances. And the image here on this slide is just a screenshot from that software, with which is kind of the main interface that we use. You know, after all that research in the 80s and 90s, LTRC transferred their cone rig over to the Geotech group here at DOTD. And there wasn't a whole lot of CPT research done after that I'm aware of, but the rig was used here in our group for production work. And from what I understand, in general, we didn't really have a section-wide push to use the cone, but, you know, certain engineers would use it on their project if it was a, you know, personal preference or for very specific applications. And when I came here in 2011, we were mainly using the cone rig to obtain design data for interstate median cable barriers, because we could go out and get a lot of data real quick. And some of our consultants were still using the LTRC pile design software on their, you know, respective LADOTD projects. And that software kind of gave us a standardized pile design methodology, sort of like the FHWA driven. And one issue with the software is that it doesn't really take overburden changes into account. And so being that most of our projects are bridges with scour concerns, it kind of limited its usage to some degree. You know, I would say within the past 5 years or so, we've tried to increase the use of the in-house rig. But kind of as we started to ramp up, our rig broke down, and it's been down, I don't know, I think since about 2018 or early 2019. But we hope to have a new rig delivered here by the end of the year, so we can kind of pick up where we left off and kind of push on with CPT usage. So next, I want to talk a little bit about a project where we use CPT, or one of our consultants use CPT to extensively do pile design. So this map shows the LA1 relocated project in Lafourche Parish. It's south of New Orleans. Eventually, this is going to be an 18-mile corridor of pile-supported highway. And although we have storm surge and wave action concerns, scour is not a design issue, so the project's a really good candidate for a bunch of CPT. The project will eventually connect Gold Meadow to Port Fouchon and the Loop oil facilities with a highway that won't be submerged during major hurricanes. Phase 1 of the project was the southern portion, which consisted of like 8 miles of elevated highway connectors to the existing LA1 that's at grade, and a high-level bridge over Bayou Lafourche. We finished the construction on that in about 2011. And we're actually right now wrapping up the design on phase 2 that will take things northward to the protection levee in Golden Meadow. Phases 3 and 4 are long-term projects that will ultimately double the capacity of phases 1 and 2. So this graphic shows the original phase 1 alignment as of about 2003 when we started the design. And so we started out with about 300 CPT soundings and soil borings, and it pretty much covered the entire alignment and the connectors. And then in 2004, we did a pre-construction test pile program, and we tested 9 piles at 4 different locations. And we tried to cover most of the potential foundation types and had everything from 16-inch square concrete up to 54-inch spun cast cylinders. And based on new structural loads and what we learned about the test pile, or during the test pile program, we did 19 additional deeper CPTs in 2007. These were done along the southern portion of the project while we were actually building that bridge, or just in advance of it. And so between 2007 and 2011, we constructed the southern portion of the project, and we tested an additional 8 test piles as part of the end-on construction. And during all this, at some point, the phase 2 alignment shifted. And so we had to put together an entirely new geotechnical investigation for the northern portion. And that one consisted of about 388 CPTs and 69 soil borings. The soil profile on the site consists of peat, normally consolidated clay, and some intermittent sand layers. The piles for phase 1 were designed using borings and the FHWA driven software, but we did look into the direct CPT methods, but I wouldn't say we heavily used those for the design. This was all pre-LRFD. We used a factor of safety of 2, and then we tested 1 pile on each bent. And then for phase 1, ultimately, we tested about 500 monitor piles and used CAT-WAP signal matching for all the pile acceptance. So the reason I'm telling you all this stuff about soil profiles and test piles for a presentation about A-GaME is that for phase 2, we wanted to know, do we have enough data and confidence to design hundreds of pile bents using just CPT direct, using just the direct CPT methods. And keep in mind, a lot of these soils are really soft, they're difficult to test. So the cone is probably at least a more repeatable means of getting soil information if you trust the direct design methods. And we did a lot more dense geotech investigation for phase 2, which you can kind of see here in this image. It gives us the ability to pretty much have a representative CPT at every single pile bent instead of having to try to make composite soil profiles from multiple borings and multiple CPTs. And so before designing phase 2, I started comparing the results of the static load tests to the direct CPT methods. And for the comparisons, I kind of broke things down into 3 categories. I had static load tests that were successful, in other words, where we failed the pile, load tests where the pile did not fail, and force pulse rapid testing on some of the larger 54-inch piles. And since we sometimes had multiple CPTs near each test pile, I used the pile driving logs to try to select the most representative sounding for each location. And also because the borings and the cones were taken from airboats, there's a little uncertainty in terms of what constitutes the top elevation of each sounding. So you have to kind of keep in mind that due to the strength disparity between the sand and the clay layers, I really had to make sure that, I selected a CPT sounding where the sand layers lined up pretty favorably with the increased resistance in the drive logs, because I wanted to make sure that if I'm comparing, estimates from these methods, that it ends up in the correct layer. And so what you're seeing in the image here is something I did probably at least once for every test pile and then for every CPT design method. The blue line is just the theoretical nominal pile resistance from the direct method. The red plus symbols are the driving resistances from the pile drive log. And the green triangle there is the failure load of the pile plotted at its tip elevation. So, in this particular case, that particular design, that direct CPT method was dead on. They weren't all this good, but at least shows that, if you have enough data to do the comparisons, you can get a lot of confidence in the CPT. So the table here is basically just a summary for those 3 categories I mentioned. And I just evaluated the quality of the prediction by dividing the predicted resistance from the CPT method divided by the tested resistance. And then so kind of what I found is that the direct methods underpredict for the force pulse rapid testing. And I don't want that to be an indictment on the test method itself, because remember, that's the only method we use for the very large 54-inch cylinders. So the design methods may also not scale well to those larger piles. You know, for tests that didn't exhibit a clear failure load, the CPT direct methods tended to overpredict. That's to be expected though, because that's kind of an incomplete load test. And then for the tests where we failed the pile and had a successful load test, the CPT direct methods actually provide a really good correlation with the static load test. So for our particular site, the Schmertman method provided the closest estimates, but it provides the highest resistances in sand. And so my concern on this project was that it could overpredict our pile capacities in sand. So what I ended up doing was selecting the de Ruyter and Barringen method for this particular site, since it appears to be a little bit conservative, but it has a pretty low standard deviation. So kind of the moral of the story here is that we have enough geotechnical investigation and load testing to feel comfortable enough to go ahead and design the entire phase 2, which is another 8 miles, using just CPT direct design methods. And that's what I've done. I just want to show this here. This is kind of a cool slide that shows it's supposed to be a fence diagram of the entire phase 2 alignment. And it actually looks like geophysical testing, but all this is the result of just hundreds of CPTs just stacked up alongside of each other. But it's really cool because you can kind of see the sand layers kind of come in and out of the profile as you progress from south to north. So I don't know how well the animation works over the internet, but I've got about 5 of these things like this. Okay, and then next I want to talk a little bit about a project where we use CPT during construction to troubleshoot some problems. So this project is a bridge widening. It's currently under construction. We use conventional borings for design, and the profile is mainly sand. We do have a stiff to very stiff clay layer between about -35 and -65 feet. There's a good bit of scatter in the end value, so we chose a pretty conservative design profile, and we also used several indicator piles before we ordered our production piles. And so what you're seeing here in the plot are the end values for the borings that are near the main span, which is going to be supported by 54-inch cylinder piles. So on this project, we recently drove a 54-inch spun cast indicator pile. It was supposed to have a nominal resistance of about 876 tons, but when we tested it with PDA at the end of drive, there was almost no measured resistance, and at the 24-hour restrike, we had only about 200 tons, which was a lot less than we expected. And just looking at the data, it looked like a pile driven into soft clay, so it didn't make sense. So we started trying to figure out, you know, what was going on, and started trying to discuss whether we needed to redesign the piles, get a new indicator pile. What exactly were we going to do? So there's a lot of scour to deal with on this project. And so even though the pile is about 100 feet long, we only have like 42 feet of penetration below scour. And so for the indicator pile, we'll usually install a casing to the scour depth, and we'll excavate to remove the side friction in the scour zone. And we still have the overburden effect to deal with, but at least this kind of gets us closer to our approximation of what the scour design case would look like. And then on this project, we found out that the casing had been installed deeper than specified due to a hard to read font on one of the plan sheets. And this ended up leaving us with a penetration below scour of about 30 feet. So we lost about 25% of our design penetration on the indicator pile. Then on top of that, we eventually learned that the casing was dewatered during excavation. So, if you drive a casing into sand and then they excavate and dewater it as they excavate, then you might expect that, 50 or so foot of head differential could create some seepage forces at the bottom of the casing and then destabilize the soils that are down there. And then so if you drive a pile into a casing that's already too long and you've destabilized the soils below that, how much penetration do you actually have versus what you designed your pile for? And then we started looking into doing another indicator pile and having them do it correctly. And then the contractor's estimate was in excess of $600,000. So we decided to look into some other options just to see if we could avoid spending all that money on the change order. So we got one of our consultants to mobilize pretty quickly and do 2 CPTs in the area of concern. And so the plot on this slide here shows the tip resistance from each of those cone soundings. And then the red line is the the tip elevation of that indicator pile that didn't work out so great. And so based on these results, the elevation of the sand, it does vary, but our indicator pile definitely should have tipped into a layer having a tip resistance on the cone of at least 300 TSF. So we somehow picked up the rig during the CPT testing, but the end of drive data from the indicator pile looks like it's a pile driven into soft clay. So it doesn't add up. And on top of that, our 24-inch square indicator piles achieved the resistance needed to confirm the design model. So in addition to the original soil borings, all these observations kind of tend to support the theory that the contractor eliminated too much embedment through overdriving the casing and dewatering it in a sand. And so we kind of decided, hey, we don't want to pay him 600 grand to do another indicator pile. And due to reasons I won't even get into, we weren't able to hold them accountable for those problems. So it was going to be $600,000, of DOTD's money. But the CPTs that we did gave us confidence that the sand layer it's indeed present, and it confirmed all of our other design assumptions other than what we saw on that indicator pile. And then we decided to go straight to slightly longer production piles with the understanding that we may have to cut some length off if we hit refusal. And you can ask me later if this ends up working out. We'll find out. And I just want to go into a couple of other real quick projects where we employ CPT here at DOTD. We have an in-house maintenance crew that builds bridges, and they use H-piles and precast concrete panels. And so their projects don't exactly follow the same design and plan development process as our typical bridges. Some of these are constructed on an emergency basis. There's generally no budget or time for typical geotech investigation. So one thing we've had to do to try to help cut down on some of their uncertainty on the materials that they bring out to these sites is to perform a couple of CPTs ahead of time, give them a pile length estimate, and then verify pile resistance with the PDA. And those, since we can deploy the CPT rig pretty rapidly, at least when it's working, we can adapt to the maintenance crew schedule because they don't offer a lot of lead time since they're on a totally different kind of paradigm than the bridge design guys. But we're able to help them out by doing some pretty rapid pile design using CPT. We also have some bridges that have been identified as SCOUR-CRITICAL. And so our bridge rating group has to decide whether they're going to get load posted or not. And the bridge design group, they'll go out and they'll get regular channel profile measurements just using a weighted tape. And so ultimately we can see how much pile embedment we actually have left after these scour events. And so the question that comes up is usually, do we have enough pile embedment to keep this bridge in service? So historically, we've gone up there and we've done borings and just estimated the remaining pile capacity. But ideally, I think what we'd like to start doing is to push cones through the deck of the bridge, assuming it's safe to get on with the rig, and to to do really local estimates of pile resistance right there near the bent in question. And this is kind of what we were starting to do when our rig broke down. We're also wrapping up a new research project that's kind of an update to the direct method evaluations that were done in the late 90s. This time LTRC looked at 22 direct methods and selected a couple of new ones that outperform some of the ones in the older software from our data set. They're also updating the software to take scour and overburden into account, which hopefully is going to increase the software's usefulness on the majority of our bridge projects. This is one project that we'll probably revisit again and again, since sites that have both CPT soundings and failed static load test are a little bit limited at this time. But when we do get our new cone rig at the end of this year, we'll be able to go back and push cones next to a lot of these old test piles and kind of recalibrate what we know about these direct methods. Ben asked me to add a couple of slides about this, so I'm going to spend a couple minutes on this real quick. But we have another relevant project where one of our consultants, Xinping with Arteman, built a geotechnical data explorer to kind of show off some of the soil boring data for one of their larger DOTD projects. And just to oversimplify a bit, it was mainly just a really nice looking web-based visualization tool for the lab data they had on that project. Being that it's a web-based tool, it can theoretically allow an engineer to view that project's data from any device with a web browser without needing Excel, Gint, Wholebase, Adobe, anything. It's all web-based. And so the image here is a screenshot showing the auto stratification tool in that piece of software and then some of the automated statistics that the app can do. And so I worked with Shin to try to broaden the scope of the project to implement digs into the web-based tool. For those of you who aren't familiar with it yet, you can go search for it, but it's basically a standard for interchange of geotechnical data. So in other words, hopefully in the pretty near future, we'll have a way to send geotechnical data files back and forth without having to worry about the source or what software it's going to be open with. And then the implication of actually working digs into this geotechnical data explorer is that you'll be able to basically open a project from any project, any location, any source, and not even have to worry about what you're going to open it on. If you have a web browser, you'll be able to look at all your geotech data. And so what's cool about this is that these data standardizations and tools like the Data Explorer allow us to process larger data sets with relative ease. And I think a lot of us probably still think about site characterization as typing boring logs into Excel so that we can plot lab tests. But if we step away from that line of thinking a little bit, these kinds of tools will let us expand our site characterization efforts and do a lot more in the same amount of time. So, you could look at things like very specific combinations of borings or data. You can ground truth your geophysical data alongside your borings and your CPTs, or even do automatic correlations or statistics just immediately once you have the data in the system. And this kind of relates to CPT because I think these types of applications are perfect for fast and repeatable and efficient tests like CPT. So what you're seeing here on this slide is just it's a screen from the software, excuse me, where they're using CPT to ground truth some ER data. And for very large data sets like this, you have to have this data interchange and these types of tools to be able to manage all that. So just to conclude here, some of our current uses for CPT at DOTD are general site characterization and delineation of sand layers, pile design using direct methods, expedited troubleshooting or exploration during construction, estimating pile lengths for bridge maintenance crews, and then deriving soil properties for applications where we aren't doing direct design methods. Some of our future goals include performing cones with an in-house crew much earlier on projects so we can scope the final geotechnical investigation. We'd like to start being able to combine CPT with ER surveys to provide a much broader site characterization, not just for design, but for construction troubleshooting as well. And then we'd like to also be able to continuously calibrate our direct design methods using new load test data, verify the SCOUR methodology that we just implemented in our new cone software, and then also estimate the resistance of pile embedment on load posted bridges. And that's all I've got. So I'm going to go ahead and turn it over back to Ben.
Thank you very much, Jesse. That was fantastic.
Thank you, sir.
The animation came through very well. In fact, I had a comment, and I concur. That was pretty impressive. What was the scale of the spacings on those CPTs for those profiles?
That's a good question. I'd have to go back and look, but for the most part, they were no further than 100 feet apart, and we were aiming for about 50 feet apart. Okay, wow, yeah. That's amazing to get that resolution on, and that's very specific data too. So yeah, it took us a long time.
Very good. Thank you very much.
Thank you, sir.
I will introduce our next speaker, Jeff Curry. Jeff Curry is with the Alaska DOTD and Public Facilities, DOT and Public Facilities group. Jeff has his bachelor's degree in mechanical engineering and mining engineering as well, both from the University of Alaska in Fairbanks. He has been the North Region Materials Engineer for Alaska since 2011, supervising the region's drilling, engineering, geology, geotechnical, and hydraulics engineering programs. He was the Northern Region Geotechnical Engineer for 6 years prior to that, starting with the DOT, the DOT and PF in 2000 as a highway designer. Jeff worked with the mining and material exploration industry in the interior of Alaska throughout the 90s, including managing underground placer mines and engineering several open cut placer mines in ice-rich permafrost. Jeff lives in and around, or has lived in and around Fairbanks, Alaska since the 80s. So with that, I will turn it over to you, Jeff. Thanks.
Thanks, Ben. Yeah, so my name's Jeff Curry. I've been Northern Region's Alaska DOT and PF's Northern Region materials engineer, and I'm also our Everyday Counts 5 A-GaME champion. We've used DOT and PF has used other A-GaME technologies over the years, CPT and OPT on occasions, project-specific cases. But my colleagues and I thought that trying to adopt geophysics would really give us a lot of bang for our buck on a statewide basis. Alaska is really big. It's bigger than Texas and California and Montana all combined. And for all that, we've only got about 5,600 miles of highway that DOT and PF maintains, which means two things. Number one, there's no redundancy in our system. If there's a road to where you want to go, there's probably only one. And the other thing is it means there's awful lot of places that don't have roads at all. In fact, over half of our communities, our villages, over 140 villages, are entirely off the road system. So therefore, DOT also does airports. We have, most of those are gravel airports in rural villages. Several of them are paved, and we have a couple international airports. Ted Stevens International in Anchorage is one of the busiest cargo hubs in the world. We also have obviously some maintenance and operations stations. PF in DOT and PF stands for buildings, which we maintain, and we also have the Alaska Marine Highway System, ferry system, such as it is. Another thing that we have in Alaska is permafrost, which is kind of a unique thing. Permafrost is ground that stays frozen year-round. Doesn't thaw seasonally. It's defined as ground that stays below 32 degrees Fahrenheit for more than 2 years in a row, but in most cases, it's been frozen for thousands of years. And it's not always a problem, but a lot of times it is. This map here of the distribution shows essentially the probability of permafrost in different parts of the state. This hot pink and dark pink stuff in the north slope is what's called continuous permafrost. Basically, you drill a hole anywhere there except like under a major water body, and it's going to be frozen any time of year. The teal stuff, on the other hand, has essentially zero permafrost. The light blue stuff here is isolated permafrost, meaning there are patches like less than 10%. There could be permafrost, but more than likely there's not. And then the mauve stuff in the middle, the lion's share, that's discontinuous permafrost, which is essentially even money. Northern region is, if you can see my cursor here, northern region is essentially everything north of that. And so we have most of the permafrost. It's a big geotechnical hazard for us. And it's really a function of what the moisture content is like. If you look at this photo here, this carrot-shaped triangular feature here, that's an ice wedge. That's essentially 100% pure ice. The soil on either side of it looks a lot like regular dirt, regular soil, but in fact it's ice-rich silt, and it's probably got a gravimetric moisture content greater than 100%. So the takeaway is you build something on this, and if it starts thawing, then you have problems. This is a typical case of this is an abandoned road that hasn't been maintained, obviously, and this is what happens. We get settlement from the ice-rich permafrost thawing, and then depending on the variability of the ice content, you get these roller coasters. If you cut into this stuff, it tends to thaw and ooze. It makes a big mess. Going back to this photo here, you see this distinct line here, everything above that. This is what's called syngenetic permafrost. Don't have time to go into that right now, but the takeaway is it was buried with aeolian silt. It's buried in a loess deposit. Sometimes these ice wedge structures have a visible surface expression. In this case, there is none. And so to locate this, or to determine that there are ice wedges in this particular location, it'd be very complicated drilling. We've drilled through some of these 80 feet of snow cone. That's what the cuttings look like. But more likely, in a case, in a configuration like this, you'd be more likely to miss it. And this is where geophysics comes in. We've been using some resistivity techniques off and on projects. When the A-GaME came along, I said, we should adopt this as a statewide initiative. Unfortunately, the Northern Region engineering geologist, who's a bit of a geophysics, let's say, expert, but he's quite knowledgeable, and he came to me independently and said, we really need to get this stuff. So I said, okay, we're going to leverage the A-GaME program and acquire some equipment. Garrett Speeder, our region geologist, consulted with an expert in geophysics in Alaska, who we'd worked with in the past. Very smart woman who had done a lot of work in cold weather up on the North Slope for the oil companies and other places. She helped us select and procure equipment, or select it. We procured equipment. We hired her to give us training, which is a really big deal. Not just here's how you turn on the equipment, here's how you hook it up, here's how you interpret the data and the software, but also the local specific, this is the parts that get brittle when they get cold. This is what you have to do to keep your batteries functional. Very, very useful. And we've basically adopted over the last 2 years. We've developed some checklists and guidance to train our new folks as they come on, and we're using this stuff. The first technology we used is passively coupled resistivity. There's only one brand that I know of that makes this. That's a brand called OMapper. And it's resistivity. I like to think of it sort of as mobile ERT. You've got a transmitter, you've got a series of antennas, a bunch of coaxial cables of different lengths, and a processing unit. And you string this thing together, and then you can let it cook and just sit in one place if you want, but you can also drag it at roughly a walking speed. You drag it behind a truck, you can drag it on foot. We've used four-wheelers. We've had good success using snow machines. It works well through snow. It works better in frozen ground than in thawed ground, so we actually get deeper readings than typically are found in the lower 48. It covers a lot of ground fast. That's the big thing, is that for doing linear projects like roads and runways, we can cover several miles in an afternoon. You have to make several passes on it, but it's still quite a bit quicker than pounding in a bunch of electrodes for ERT work. Because it's so fast, we're able to do alternate alignments when we're considering moving a road or an airport to a new location. As it turns out, ice has an extremely high resistivity, and ice-rich permafrost, ice-rich frozen ground, also has a high resistivity, and of course thawed ground, wet ground has a very low resistivity. So we get pretty good contrast. Here's an example of a project where with ERT, with CCR data and drill logs. In our drill logs here, the black zone, that's our symbol for ice, pure ice. In this case here, where it's only halfway across, it's 50% visually speaking. But you can see that these ice, of the borings that go into ice do reflect these high resistivity zones, whereas this thawed zone does not. And this is one of the great things about combining geophysics with drilling is, normally you would have to look at this and say, okay, so we're in ice, we're in bad ground here, we're in relatively good ground over here. So where do we draw the line here? Well, we could drill more holes to try to define where the break is between there, or we might just arbitrarily split the difference, or maybe be real conservative and put it over here. But this gives us the picture. And in fact, We don't have any holes that are very close over on this end of the section, but we do have a very clear distinction between where the ice-rich permafrost is and where it's not. This is a big deal because we might decide to do some pretty exotic construction techniques to try to keep this ice-rich material frozen, and we don't want to do any more than that we need to, so we can kind of optimize our designs. The other thing we can do is we can do the geophysics before we do our drilling, and we can target specific locations, specific anomalies, as well as some control locations, and we can get a better data set, a more complete data set, ground truth it, and still do it faster and with less drilling than we would have otherwise. The other technique that we use is ground penetrating radar. This is not terribly exotic stuff, but we've used it, and it turns out we use it even more often than our CCR work, which is primarily for frozen ground and occasional water tables, things like that. Ground penetrating radar, of course, measures dielectric permittivity, so it's good for looking at different layers of materials. Voids, great for finding voids and culverts. It's good for identifying a water table. It works great through ice, and we actually use it for ice to confirm that ice is thick enough for us to run our drill rigs across when we're crossing water bodies. It's great for measuring asphalt thickness with the right antenna configuration. We have places where, because of our settlement, we've got asphalt patches that may be several inches thick, maybe several feet thick, maybe tens of feet thick. And by using GPR, we can determine what the asphalt thicknesses are, which affects some of the different treatments we're able to do, or the construction techniques we're going to use. We also use it for utilities a lot, for doing utility locates. We have urban settings where utilities are poorly documented. And so bringing our GPR unit out lets us find a safe place to drill for in urban conditions. Now we take our GPR unit with us on almost all of our drill programs. So here's an example of ERT, and this is the Nome runway in Western Alaska. It's a very complicated geology. The runway is built partly on dredge tailings, partly on virgin ground, partly over the Snake River, which was backfilled. It's got a lot of different conditions, and it's been built and extended at different times. And this pretty well shows some of the different properties. There are drill holes that go with this data too, which is important. You don't ever want to rely on geophysics exclusively if you can possibly help it. But let's go through the benefits here. This is fast, and when we do either CCR or especially GPR in the field with our drilling program, Northern Region has its own, maintains the state of Alaska's in-house drill program. When we're doing that, inevitably there's some downtime when whether the drillers are tripping out or moving between holes or servicing the rig or something. So our engineering geologists can get out ahead of time and collect data and essentially add very little time to our programs. It's convenient. It's all packs up into some Pelican cases or in action packers. That means we can mobilize it out of a vehicle or out of a small aircraft. We routinely will do work for our maintenance and operations folks, do forensic stuff, and maybe we can do it in a day or even just an afternoon, or do utility locates for a construction project. It's very helpful. The real-time data allows us to spot holes better, so we get better data. We drill holes smarter, not more frequently. We can ground truth those anomalies and reduce the number of drill holes that are required. We fill in the gaps between the holes, which gives us a lot more information. We're really reluctant to try to draw lines between holes because you don't know what's going on between the holes. So now you've actually got data that's legitimate data that you can plot with your drill borings. That gives us more information, allows us to optimize those designs, and it reduces the surprises. It reduces the risk, and that results in lower bids and fewer change orders. And finally, these graphic outputs, I find them to be really helpful. They really help you communicate the distinction of what's going on here. Okay, here's where the water table is, where the water's flowing through the embankment here in Knowlton. Here's where we've got, clearly different conditions, and it really helps you communicate that. There's obviously some costs associated with this. We have probably a little over $100,000 worth of equipment and software invested at this point. You want to have training. I emphasize the value of having an expert train you hands-on with local conditions. So the ability to get all the hard knocks education that our expert passed along to us has saved us a lot of time and a lot of frustration, broken equipment, and being stranded. We use this stuff at 20 below sometimes, 20 below Fahrenheit. And so knowing what's going to behave properly, how to keep your batteries functional, things like that, very important. There is some extra analysis time in the office, depending on how much analysis you want to do and how much extra work you want to do. That can increase the time of report writing. And really the main key is having a motivated staff and a champion. Say our regional engineering geologist came to me independently and said, hey, we need to do this. And he has ramrodded really the whole project. I give him a lot of credit. Our engineering geologists and some of our other folks, they want to do it. It's a volunteering program. Nobody's forced to do geophysics. Everybody wants to. We've been training the other regions as well, and we've loaned them our equipment. We're working on trying to get equipment for all the regions in the state. I think that's all I have. Let's see here. So I'm going to give it back to Ben now.
Excellent. Thank you very much, Jeff. That was a great presentation. Just love the coverage that you get, and one of the states where GPR is highly effective in your conditions, and great to see that working for you. Great presentations, everyone. I appreciate it very much. We have had some questions come in, and it looks like my colleagues have been on it. They have been answering it in the question answer pod. There was one question that I don't think was answered, and I just want to make sure I didn't see it. So this question was for Jeff. The question was for seismic refraction. Can the strength of the signal or of the seismic generation source overcome ambient seismic interference?
Yes, quite often, but occasionally you get a site that is just so noisy that you can't get through it.
Gotcha.
And that's when we try to work either off hours or you have to completely stop. If it's traffic, you have to stop traffic.
Yep. Gotcha. Very good. And probably it's so just a shout out to all of those in the audience. If you have questions, please feel free to populate those in the chat pod or in the question answer pod. I think what we'll do is just sort of revisit some of these questions, make sure people saw the answers, because quite honestly, I did not see that Jeff responded. And I'm just another shout out to Daniel Alzamora behind the scenes today, helping me with questions and keeping me straight here. There was a question asking Jeff about the abilities of geophysics to differentiate soils, clays, sands, peats, and how geophysics can be used to get soil information for that purpose. Jeff, do you want to just sort of talk through some of the fundamentals there?
Sure. Yeah, geophysics can be used to differentiate different soils and give you basically a soil profile, but it's going to be dependent on a couple of things: how deep your depth of investigation is, whether we have a contrast in the properties of the soils. You need to have a contrast, whether it's density if we're dealing with seismic methods, or conductivity or resistivity if we're dealing with something like radar or electrical resistivity. You have to have that contrast in order to be able to detect them. And then again, we get back to the issue between detection and identification. You still need a boring or two along your profile so that we can then correlate those changes we're seeing in the geophysics to true stratigraphy.
Very good. Thank you, Jeff.
Yep.
There was a question from Jesse that came in, and I'm not sure if everyone if you're seeing the questions come in or not. So you may also have these questions if you're not seeing them. The question was, does Louisiana DOTD use CPT or seismic CPT for settlement estimations?
Yeah, we haven't had seismic capabilities as of yet. We hope to have that capability with the new rig that we're going to get. But just in general, I'm not saying that, that it's as a rule that we don't do it. We just haven't used it for settlement estimates in the past. We've done some dissipation testing, but honestly, we lean more towards pile design and site characterization, and settlement estimates. We pretty much go back to consolidation tests. So, we can't get rid of our borings completely because we like to have those Atterberg limits and consolidation tests to kind of correlate it back to.
Very good. Thank you, Jesse.
Yep.
A question that came in for Jeff Reed was geophysical study done. This is for the project that was done on the rock slope. Were the borings drilled for each survey line, or at least one or two borings, needed to drill for each line on the slope for calibration? Or was it unnecessary to drill borings for each line for calibration?
Right. So for the H/V data, the borings were put in where they could be put in, and we got calibration points at each of those locations. Obviously, the more calibration points, especially for H/V, the more calibration points you have to properly address the calculations you need to make, the better, the more accurate the resulting topographic map will be. For seismic refraction, we don't necessarily use the boring data to constrain the models. We use the boring data to assess our error. So we don't need to have borings along every line. We just need some scattered throughout the area, close to lines, so that we can assess what kind of error we're actually seeing in seismic refraction data.
Very good. Thank you, sir.
Yep.
And there was another question for you that was asking for recommended references or links to basic information on geophysics.
Yeah, there's an older reference by Telford, Gerhardt, and Sheriff. It's called Applied Geophysics. It's a pretty good, all-encompassing textbook.
Very good. So that provides background on the fundamentals and
about the theory and use, practical use. It doesn't get into newer equipment because it's an older textbook, but it
Gotcha.
gives a really good sense of theory.
Well, that's good. That's one that I have not looked at, so I certainly am interested in looking at that. There is a geophysics manual that was put out. It's a reference guide from FHWA back in 2002, 2005. It was meant to be a web-based tool. We are working on getting that through our public affairs and 508 compliance, so that'll be back out. It was meant to provide some basic guidance and also be applications based. So if you had a specific problem that you were trying to solve And so you would enter it from, you could enter it from that perspective and say, what tools can provide me or are most likely to provide me some good information. So interactive, and we're hoping to get that web-based tool back out there to help. There are some matrices also that are from multiple sources that can help with sort of what tools might be good for different methods. But this is, it sounds like this might be a good read for me to catch up on for the reference that you suggested. And I'm looking to see if there's any other questions that have come in. And Daniel, you can, if you have seen any, I have not seen.
Hey, Ben.
Any.
Yeah,
Yeah.
there's one that came in. Jeff mentioned the ideally the depth to bedrock would be 10 feet minimum for seismic refraction. What method would be best to use for sites where bedrock is very shallow and are undulating?
Probably ground penetrating radar, but it's going to depend on soil type. It's really the only choice for high resolution in the really near surface. If you have granular soils, even silty soils, 10 feet of penetration is not difficult. If you've got clayey soils, you may not have adequate penetration even at 10 feet. But there's really no other method that's going to give you the vertical resolution that's really required when depth of bedrock is less than 10 feet.
Thanks, Jeff.
Thank you.
One other question, and Jeff Curry answered it, but maybe Jeff Reed has some additional or information on it. What is the minimum crew size to run a geophysics survey? It doesn't look like a one-person job.
Good point. Occasionally it is a one-person job. If you're doing ground penetrating radar, for some of our work, especially DOT related work, we can link GPS with the GPR. You're essentially all encompassed. One person can run the survey. Obviously, seismic surveys, electrical resistivity surveys, where you're installing electrodes in the ground, we typically use either a 2 or 3 person crews. Unless it's very large, then we might go to even more. But I'd say generally we're usually two person crews.
Very good. Thank you, Jeff.
That's everything I saw.
That's everything. Okay, very good. So in this final 2 minutes, I just wanted to remind everybody, trying to find my screen here, that we do have a webinar next week. Actually, it's a double header. And it is on the geophysical methods, and Jeff mentioned this to you. So we will be having a double feature talking about seismic methods from 12:30 to 2 Eastern time and seismic methods from 3 to 4:30. We will have a number of excellent presenters. Those presenters and panelists will be available to field questions both during the session number 1 and 2. All presenters will be available for that. So we hope you can join us next week. We'll be talking about exclusively those methods. We'll be also highlighting where we can get advantages, as you saw here in today's presentation, where multiple methods and techniques help us characterize, and very typically that is the way to go. So with that, I want to thank all of our speakers today. Excellent presentations, and hope you can join us next week for webinar 5. Thank you very much, everybody.